Get program website. And then we're going to add words. And then okay. Okay. So, hi everybody. Let's we have a short agenda today, but you see this. Okay, I think you all have, well, no, you don't all have. I sent lots of program return to you. 4 of you gave me erroneous email in the bounce back, so I don't know what to do with them. Oh, and one person gave me no email, neither on the programs nor in the concept test. The person's name was there, but 4 of them bounced as it being invalid mail. Okay, so if you didn't get your program back, probably you should email me and say, I didn't get my program. Check and see if I'm on the bouncing list. All right. I'll give you the curve very soon. One more announcement is there's a program to make that uses GDB. So you need to practice. It's the old story of reading the driver manual thoroughly and fully understanding the driver manual doesn't say you know how to drive a car. You have to do it. So seeing me talk about GDB doesn't cut the beans. You actually have to do it. So there's a program there. You should try it, and it's representative of a final exam program. Okay, it's number 5. It's the last one of this year. Okay, so let me send you all. Now you deserve to know where you stand in the curve. So where did I store that? Let's find it. Well, I'm looking for it. I think it's here. I think it's here. Probably here. Midterm score curve. Okay, hang with me and find out how we do this. Curve. Okay, over here. So it's in the chat messages. You can find out your relative standing. Let's see, I'm trying to remember. I finished these many days ago. I can't remember. Usually there's some lessons learned. In programming, the biggest loss of points is attempting to do too much. Whereas doing part of the specification and getting 50 or 60 or 70 points that actually works, the program has to actually run, is better than a non-running program that gets you 5 points. You already know this, I think. Don't bite off so much that you can't completed. Uh, it's intended to be that way. If the problem was so trivial that everyone had 100, it's a meaningless measure of your learning activity. It can't be so hard that nobody gets any higher than 0, and that would be meaningless too. So the program that I send you is kind of difficult, but it's doable if you do it in pieces. You look at it and say something like, I don't have time to do data validation. I never really understood that one. So I'll do the rest of this trig problem. That's how you should approach those programming assignments. Okay, let's leave that. Any questions? So we have 2 things to talk about. There's this number 5, the problem of adding numbers. Let's address this one. It's a spinoff from program number 4. So large, I'll title it large plus small. And it relates to program 4. In the end, it will relate to it. So in some realms of science, other than computer science, I don't think we have this issue. But in the study in earth science and physical sciences, it apparently comes up more frequently than we know of. And it's the issue of scientists is adding together quantities, maybe weights of electrons, weights of atoms, molecules in a gram of carbon material. You're adding up small quantities, but when you add them up, millions of them, you get a large number. See, so there's the issue of adding things. It could be subtracting, it could be multiplying, but we'll just speak about adding a large number and a small number relative to each other. Okay, so 1 million and the number 3, there's a large and a small because there's a relative difference between those two. Okay, well, this creates a problem for computers because, the mathematical work is done by a machine and it gets it wrong because it doesn't know how to add. It's not able to add large and small numbers. So I'm going to make an example. And I picked good numbers, I thought, before we started. I want a number that's not computationally intensive. I don't have it here. Let me see. I know I wrote something nice down. I can't find it. Well, okay. I'm going to pick a large number. And let's make it, what should we pick? 11? No, that looks like binary. Okay, we'll take a chance. 12 times 2 to the 7. And for small, we'll pick 8 times 2 to the minus 20. It's kind of tricky to get the right distance between a large number and a small number. But we're going to attempt to add those two together as if we were a machine, not a math major, but how a machine would add those two together. Was all this? Okay. So and one more assumption, just so we practice 32-bit IEEE numbers. Let's solve this problem in 32 bits. So, 32-bit machine. All right, let's start with our large number. I want to get it into scientific form is the basic thing here. So L for large. 12 is what? 1100 times 2 to the 7. Hope that works, which is not quite scientific. It's 1.1 times 2 to the 10, I think. Okay, I'm looking at my answers. I think that's binary scientific. Okay, let's take the other one. The S is for small. That's 8 times 2 to the negative 20. 8 is, this is kind of dumb. 8 is 11100. 1000 times 2 to the minus 20. And so we're going to move the decimal point to 1.0 times. This got smaller. This got smaller, so that one has to get larger. 2 to the 6, negative 16. No, I moved 3 places. 2 to the negative 17. I think that should be it. Okay. So what is the large? The large is okay, what do we have to do? To make this addition happen, you really need to have the exponential part equal to each other. If this exponential number trailing and this one the numbers were adjusted in such a way that these two matched, then we can add the coefficients in front, and we'll have an answer. So I have to make those match. I think I want to work on this small one and shift the point to such a place that that what's in the exponential box matches that one. So that looks like from negative 17, I think I have to go 27 places. Okay, here, that's a lot. 0 point. It's dots here, so I have to have 26 zeros. Well, this is and there's 26 here. Okay, so the dot was previously here, where the red is, and it moved 27 places, making the number smaller. Then this one has to grow 27 places larger. And that's our small number. Okay. So now, I don't know if I picked good exponents to make this example work, but we'll see. Okay, so now we're going to line them up. See, they both have the same exponential factor involved. That one and that one, they match each other. So if I line them up, it would look like L equals 1.1 and useless zeros all the way across the page. 2 to the 10. And directly below it, I put S, the small number. And here it is, just by my finger, 0.0000. And this one terminates in 001 times 2 to the 10. Well, they're lined up so we can add them. A machine would do that. It will line up to the bits. Actually, it doesn't move something physically, but it keeps track of where the point should be and what the exponent will be. So here is the sum, SUM is 1.1, adding those, 0, 0, 0, 0, 0, 0, 0, 1 times 2 to the 10. Okay, now what's the count? The count is from here to here is the 26th place. I underline that. Did I say that? Actually, 26 zeros and then the 1. So out to here is position 27. Okay, or here is 27 bits. Okay, and now we want to put that into a IEEE register. First thing you do is you take 10 decimal and add it to the bias number. Bias is 0, 1, 1, 1, 1, 1, 1, 1 plus 10. 10 is 1, 0, 1, 0. And we add in the usual way, 1, 0, 1 carry, 0, 1 carry, 1, 1, 1 is 1, 1 carry, 0, 1 carry, 0, 1 carry, 0, 1 carry, 1. Okay, so we have a stored exponent. And the mantissa is up above, staring at us right there. And I think you can see the punchline coming. When we write out the sum for the register, it will be the sign, the stored exponent, 1, 0, 0, 0, 1, 0, 0, 1. And just put a little mark that this is where exponent ends. And then here's the problem. You have 23 bits to store that exponent, which to store that mantissa that has 27 bits in it. So it will start out, and this is hidden bit as usual. It'll start out, the mantissa starts out with a 1, and then all zeros. Then you're at the end of the register. That's the 23rd, 24th, 25th, 26th, 27th is the 1. You saw what happened. I added this small number to a large number, and the sum didn't change. It just remained the large number. The addition was useless. I'm going to actually put this in hex because we need to practice. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And 1, 2, 3, 4. Okay, so it's 4, 4, C, 0, 0, all the way down. So here's our answer: 0, X, 4, 4, C, 0, 0, 0, 0, 0. Okay. The problem arises from the fact that the distance between two numbers being added is too great that the smaller one will no longer fit in the given register. Okay. Now this problem probably could have been solved in 64 bits because there's more bits in the mantissa, it could hold it. But even there, if the numbers are far enough apart, 64 bits still fails to do the job. You follow the story here. When you go to write out the small number, it has to match the exponential factor. To make the addition happen, these two have to be the same. So you slide the point around so as to make these two the same, and then you can add in vertical columns across there. When you do that, complete that adding, you'll discover, many times you'll discover that the mantissa of the new sum will not fit anymore. There's a loss of precision and it just gets thrown away. And what you think is the mathematically correct sum is not the mathematically correct sum. That's a case in point. Now, this happens more than you know about. It happens in physical sciences. Scientists is adding, they collect data and they analyze it with a computer, and maybe they're collecting the weights of electrons, the weights of protons, the weights of long chain carbon molecules, and they collect all this stuff together, and it's in data form. And included in there are weights of marbles and pencils and erasers and tablets, and it gets all put in there. And for whatever reason, scientifically, they want to know what's the weight of the combined mass. Okay, well, you run a machine, a computer that adds all those numbers together, and it gets wrong numbers. Why? Because the weight of a marker here compared to the weight of a nucleus of a hydrogen atom, the difference is so humongous that adding them together gives you wrong answers. Like my little problem here, gave wrong answer. Okay, so what does that have to do with assignment 4? Voluntary assignment number 4. You don't have to do it, but it's a good thing to do it to get a good grade. In number 4, you start out adding, how does that start out? You start out with 1 is your total, and then you add a half to it, and your total is this. And then you add a third to it, and your total is this. And then you add a fourth to it, and your total is 2.088333. And the sum is growing, but its growth rapidly slows down to almost nothing. I don't know the numbers after this, but it keeps going to something else, 2.22. And after a while, your sum number may be, say, 18. And you're about ready to add to it 1 over 1 billion. The spread is getting to be significant now. And the chances are very high that not all of this 1 billionth is going to be included in there. The 1 billionth number will have a form that looks like, in decimal, obviously I don't know. Oh, 1 over a billion is what, 9 zeros and a 1. Okay, well, that was easy one. I think something like that. But what if your terms go on and eventually it's your 1 over 13,786,492,571. 71. And then expressing that as a decimal number, you have some odd thing that looks 0.0000. It's getting smaller and smaller. 8476922. It looks all those zeros, and then this one, and you're going to add that one into here. You're starting to face the problem of what happened in those 32 bits a few minutes ago. What will start to happen is it truncates these small digits, and you keep those and you add part of your value in there. So I've used, for programming practice, I've used that harmonic problem a number of times. It's a famous problem, harmonic sums. And I think that nobody knows the answer. I mean, worldwide, I don't think anybody knows the answer, because the true answer is lost no matter which computer you use. If there was a special supercomputer that had 512 bits in a register, eventually this number gets so small that it starts to, even that machine starts to lose precision. So harmonic problem is assignment number 4. It's a good exercise to build, but I don't think anybody knows what the real sum number is. What is the real answer? Okay. So in past semesters, it was one semester I made it a mandatory requirement. You had to run it to 10 trillion. The ending number was 10 trillion. And at 10 trillion, your sum is around 30.5. By the way, that takes a couple hours to get to 10 trillion. It's about that, but nobody, oh, it's that, and there's a lot of other digits. I don't know, but I once had them written down. But personally, I don't think it's right. I don't think the answer is no, because of the small, tiny fractions that are lost a million times over. You keep losing a tiny fraction of your added in number, and therefore whatever they got, it's probably accurate out here, but nobody knows what it is out here. Someday you may program on a team for a science research project and run into this issue. Maybe it's not harmonic, but it's some other kind of addition of extremely large and extremely small numbers. Okay, any questions? I think you're okay. So if this shows up on the concept test, you'll know what to do, won't you? Okay, good. Let's address the second half of today. What was that? That was the demonstration. Okay. This is kind of interesting. Okay. So yeah, I like reading technology in a document. That's great, but it doesn't really come to be part of you until you see it and touch it. So I told you in the past about a linked list of activation records. And it probably sounded like some gobble garbage and go over most people's heads. That's expected, but we're going to try and see it. So what I have is, let's see, there's a main function here. I think it was called S0, and it calls, and these are just kind of junk functions. They don't do anything valuable. It calls S1, and then this calls S2. And it went to, I think it goes to S3. We'll find out. And then it stops. Okay, so on this, off to the side, while that's visually happening, out of view is memory. So there's, how can I draw? Two parallel lines represents memory. So this one starts up. Let me see if we use another color. When this is main over here, S0. M-A-I-N. Okay, main starts up and instantly for all the static variables, it creates an activation record, which will show by this green box. And remember the back end has got a lot of zeros in it. Okay, and then next one comes along and a different color. S1, S0 calls S1, and then it creates, that calling creates this space. Okay. And because the compiler can read the size of every declared variable and declared array, except dynamic arrays, it can't read that one. But it can read the size of everything else. It knows how many bytes to make this here, this space here. All right, and now the back end here holds the address of that one. That says this in data structure style, this would have an arrow that goes out here and connects to here. I think that's how they do
Hello,
it.
Professor.
Yes.
Sorry, are you going to go over the programming section of the midterm during this class?
The programming section.
Yes.
I don't quite understand the question. What is there to go over?
Just like the exam in general, like walking us through how you would have done it.
Oh, yeah, I'll do that after this little session is finished. That doesn't sound like test material though. This does sound like test material. Okay, but yeah, I'll do that if you wish. Remind me in 10 minutes to deal with that.
All right, we'll do.
Okay, so somewhere along the way, S1 calls this one, and it starts a new activation record, and I'm going to draw it in here. It goes here. And it gets, as it's back in, the address where this one is, and I think the data structures experts draw a line that says, if you own the address of some other place, then you're pointing to it. So it connects like that. And then finally S3 is called, and you get another activation record created. And it's back in, has the address where he is. And so we show it visually by an arrow going and connecting with that one. And then one more is RBP sits over here at current time, and it has the address of that one. So actually it has an arrow that leads to there. Okay, so out of that is, okay, out of that picture, here's the front pointer, RBP points to this activation record. We'll call them A, B, C, and D. There's A points to B points to C, and C points to D. And D, did I mislabel? Sorry, everybody, I'm just going too fast. This is D. I think the letters are wrong. This is C. This is B. and that's A. And A has all zeros here, and that's the null pointer at the end of the list. Okay, that should look like a standard linked list of nodes, but we experience them all buried inside of memory. Okay, I'll run this quickly and get, we can, actually, this is a test question from the past. So see, I want you to miss the points. I want you to get the whole points. Okay, I've got to find the program and run this. Where do we get it from? It's lost my folder, but I'll find it. And we gotta go teaching and teaching where I'm going to share the screen with you as soon as I identify where we're going to be, which one is going to be stack frames. I think this is it. And okay. Okay, stay with it here. Okay, I have to move it to workspace number. What number is this? 3. Okay. I think that did it, and then this one did it. Workspace 3. And here. I still don't have it quite right. It has to be in the same workspace where Zoom is. That's the whole thing. It's not here now, but I've got to find it. Not that one, not that one. Okay. Four. I think we're getting closer. So let me try. CLEAR. Okay, we're making progress. Share the whole window here. Okay, I think you're seeing my desktop, and in front of us is this is a very messy file, a bunch of files. We won't even look at them because they're not that interesting. There's a program all in C++ called SF0, and it calls SF1, and it calls SF2, and it calls SF3, and SF3 doesn't call anybody. Here's what it looks, they all sort of look the same. A bunch of declarations that don't do anything. And then it says, show me the stack here. This is not GDB, this is plain old programming. It says, show me the stack. This is a stack number 401, 2 quad words outside of the stack, and 26 quad words inside the stack. Small stack dump. This right then I commented that out. Soon after that previous stack dump, here's stack dump number 490, 2 quad words outside and 222 inside the stack. That's turns out by experience 2 hours ago, that's way too many. Let's just go with 120. Okay, and save this. All right, all 4 programs are just kind of stupid stuff like this. They're built as an exercise to view the linked list of activation records. Okay, so where's the terminal? There it is. -L. And we should do this. stretch it out a little bit more. Okay, shr.sh. So looks okay. All right, it all happened. It flies. This does not pause like GDB, but let's see if I can go back to the beginning. Okay. Yeah, here's where the run started. Okay, it dumps out all the registers for you to look at it. And that's happens in some of the early functions in that list of 4 functions. Here is, I think we're working with that. Number 401, stack dump. Here is RBP's value. Here's RSP's value. Here, this right side column are the quad words on the stack, but not, these are addresses on the left side. So the data are these on, I can't get one at a time. These are the values in the stack dump, okay, memory dump. Okay, but 401 was not our main interest. Our main interest was the next one, item number 490. And there is the back. Remember, for the linked list, that's the front, that's the pointer that gets it all started. This one, it hangs around, but doesn't play a big role in determining that linked list. Okay, so here's all the values, all these quad words in memory at the time that was called. Okay, now that's a giveaway. The software was built to put a 0 marker at RSP. So if we go back and look, you'll see RSP ends in F1, or is that FL? F1A0. F1A0. There it is, F1A0. And it's marked as byte number 0. Okay. And as you enter into the stack, then it counts by byte 8 inside the stack, byte 16 going inside the stack. And there's 2 of them outside the stack. They're outside the top of the stack. Okay, so the question is, this is we're looking at a test question from a year ago, 2 semesters ago. The question said, find the linked list. So I want you to get full credit for it. Let's see, how would you find it? You should find something that contains addresses on the data side where the address appears on the left side. And so visually, it looks like an address. 2CF1LE, 2CF200. Is that a candidate? 2CF200. It looks pretty much like it's right here. Now, when I click on it, the green marking is going to disappear. It's that one. Okay. And let's see, did this one appear anywhere? F1E0. Yeah, it's right here. Did that have a predecessor? I don't think so. This address never appeared. Oh, we can't go outside the stack. Don't look beyond there. Okay, this looks like the back end of the current activation record. The back end contains the pointer, remember? A little diagram I drew a moment ago. So from the front to the back is all of that. Okay, at the back, you'll find an address, and then you go trace for that address over here. E0, right there it is. Okay. So that becomes that marks the back end of the next one. So the next one went from where we left off. I lost here. I lost my place. The green marking doesn't want to stay there. Okay, here's the back end of the first one. And from here, it's the front end of the previous one that goes all the way to here. Okay, FL. And then this will be the back end right here. This is the back end of the previous one. So that one goes all the way to 200 right there. And then the contents at that location is where this one, now this is still part of the old one, but the new one starts here and goes to 230. 230. And at 230, you look at this where you'd like to find this address somewhere over here, but guess what? That's the null pointer. There's nothing after it. That's the end of the linked list. There's supposed to be 4 functions called and 4 activation records. Can you, if you had to do it, you could do it now, couldn't you? And so let's take this. We go until we have, the front end is harder to find. Let me just, okay. I lost my place. FLE0, FLE0. Yeah, it went to here. So there's the activation record that's current. It's currently executing. No, I actually put I'm missing one. It starts here. Okay. That's better. Okay. How do I know? Well, you look at back ends. This back end contains F1E0. F1E0 is up the page a little bit, F1E0. So the front end of the predecessor is that address that will execute next. And that's typically a very small number, as you can see right here. So this one goes from here to F1E0. There, I've got it. That's the second of 4. Right before it is an address that will execute when return reaches this activation record. Okay, so it goes from here until 200. Okay, and that one then starts a new one and it continues to 230. It goes from here to 230. And that's the 4th one, but this one has no place to go to. Address number 1 is inside the operating system. It's not a valid address for programming purposes. So there's the 4 of them. You okay? You see the question on the concept test? You won't write, you're not going to write blank right away. At least you should try and find it. Okay. I think I'm done. I'm done with this discussion. Someone asked a discussion about the program part, and we can go for that in just right away. Okay. Did this get shared? Yeah. Okay. Stop and share. All right, that's the agenda. Okay, so the question was, I see a question on the chat messages. Okay. Let's go. I need to bring the question in front of me. I'm gonna what the programming problem asks for, and then we'll discuss it. So I'm gonna close all this old stuff and let's find question about 223. 220 summer, 2 springtime, 240 test. Okay, okay, it's here and share screen. And here's our take-home programming test. And just going over it, where to deliver it, don't send executable files, and that kind of stuff. You don't have to do that, all that documentation. I just want your name and email address and section number. We're in section 5. Okay, what was it asking for? Oh, okay. So there are 2 inputs, hours worked and pay rate. And from that, you compute total wage for the week. And there's a little formula up here, hours times rate equals gross pay. If you're under 40 hours, if you're over 40 hours, it's you get a bonus called overtime pay. And overtime pay is like the number of hours over 40 times your pay rate times this bonus factor 1.5. Stupid little formula, but even if you got it wrong, my interest is that you made a good program out of it. Okay, so here's a sample run. You enter name and the pay rate, dollars per hour, and the hours worked. And then it computes 3 numbers down here. Regular pay is what you get for the first 40 hours. The overtime pay is what you get if you work beyond 40 hours. And total pay is what it says, it's total pay. Okay. Did I give us, I didn't even suggest, sir. Oh, I did. Yeah, I did suggest. Let's see. I did suggest 3 blocks here, but you know, that's what I'm really looking for is show me what you can do. If you didn't do this structure of five pieces and you did it in a different way, and it looks good and it produces good answers, hey, I might give you 100% or something close to it. But many people ask me, how do I get started? Well, here's what I would suggest. Getting the 2 numbers. All this one does is input 2 numbers, hours worked and pay rate, and send it back to this guy. What does he do? He has to do a little formula. You use one formula if the hours is 40 and less. You use a second formula if the hours is 40 or more. So this is the work down here. And he sends back the amount earned, the gross pay, they call it. And so this guy up here says, okay, let's output the gross pay in a nice way. And that's your paycheck. That's kind of a reasonable partitioning that fits human knowledge, human subdivision, dividing would sort of come up with something like that. I suppose there's other ways to view it, but I think that's what would come up in most people's minds at the very beginning. So sample dialogue, I think these numbers are correct if you wanted to run it against it. Okay. Oh, this had invalid inputs. You know what? I don't think a few people did this, but it was a minor deal to me. I think I even just, if you didn't do invalid testing, I think you still got credit for the whole thing. And what was, how did it end? Summary, oh. I just added notes from the previous Tuesday before this test happened. You could do fine without these notes. Is there anything more? And where to send it to? Okay, that's pretty clear. There is somebody else with my same last name, but he spells it differently. I hope you didn't send your test to him. 4 people gave me fake return addresses. I assume you just hit the wrong key. So 4 of them were never returned. I'm waiting for you to email me and say, can I have my test back? Then I'll know where your address is. Okay, so what would anyone like to know about this program?
Well, I had a problem with my, I got the email and it said that my bash file wouldn't run, but I use Tufix, and when I run the bash file on my system, it runs the program fine. So I'm not sure what I did wrong.
Oh, no, maybe you did nothing wrong. The machine I'm using seems to, you're not unusual. About 5% of all the submissions I get just doesn't run. I move it someplace else and it does. So here, what I need from you is send me a mail message with your name and say, please run my program on a different machine. And I'm glad to do it. This has come up 5 times this semester. You may be fine.
Okay. Thank you, Professor. Yeah, I'm not sure what's going on. I sent I already sent an email with like screenshots showing like the program running on my end and everything, if that helps too.
Yeah, you're not alone.
Yeah.
Throughout this semester, it's not a large percentage, but there's 5%, 10% of you. I don't know. It's a hardware problem. And if you tell me that it ran good on yours, I'm glad to do it on my other tower machine. And it usually runs then. But let me know, and I'll do a second run somewhere else.
Will be.
Okay, but I got to hear from all of you. Anybody else have issues like it runs on my computer and I'm using Tufix or WSL or other base like that? Then same thing, William says. Yeah, hey, Williams, also send me the message and say one sentence, you need to run my program on a different computer. And that's okay. I'll be glad to do it. So your issue was not about the structure of the program or how to approach it. It was the fact that I gave you bad feedback when it actually did run.
Yeah. I wouldn't call it bad feedback. I'm sure it's just like a technical issue. So yeah, it's not like you did it on purpose or anything.
Oh, no, I don't. I wouldn't do it on purpose. No, I have a nice laptop, but in all other respects, but about 5% of bash files, it just screws them up. I don't know why.
I do have a theory. I did it on Tufix, but I did the drag and drop from my virtual machine to Windows, and then I emailed it from you to Windows, or from Windows, to the email. I'm not sure if that could have messed it up in any way or anything like that.
I don't. How can we test for that? I don't think so, but if it comes back on a second Linux computer, then I'll have you resend it. But I don't think it'll come back bad a second time. Let me do a second test run. And so you've identified yourself in email to me this afternoon sometime.
Yes, I sent it about an hour ago.
Sounds good. Sounds good. I'll get to it tonight when I get home. And so as a general policy, everybody, if I make a mistake, I'm more than happy that you tell me, look, you didn't add my points right. look, you overlooked one of my questions and didn't assign points to it. Look, my program runs really fine on my computer. That's someplace I made a mistake. If it's your mistake, hey, teacher, I didn't send you all my files. I'll send them to you 2 days later. That's not a mistake on my part. That's a mistake on your part. So mistakes I make, tell me about it, and no hard feelings. I'm happy to do them again, regrade it again. Some of these were graded staying up late at night to 2:30 in the morning, and I was pretty tired at times. And I could have had mistakes along that way, especially concept tests. They took way late at night. I wasn't sure what I was seeing. So you gotta tell me, and I'll work with you to make it right. Okay. We're done with lecture today, everyone. There's 2 weeks or thereabouts remaining this semester. Pretty much each lecture, I'm just going to pick some territory from earlier this semester and review it. So next class meeting, we'll start officially reviewing for the test. Anything else from anybody? I don't need to share this now. Okay. If you wish, you can private email. You can private message me. I'm going to stay around, but lecture has ended, and you're free to do what you want to do. So if you wish to, the finals be like the midterm. Yes, Greg, the concept test is the last Thursday of the real semester, the last Thursday before finals week. And the programming test is during finals week. That's just like midterms. We had midterms, we had a concept test before the spring break, and then the program was after the spring break. Okay, you're okay. Yes, the same. I'm just going to be here, and everybody should download the last programming problem of the semester. In content, it's very short. Compute the third side of a triangle. It's the GDB part that you'll be experiencing as new. Okay. Okay. Yeah, hello. I'm watching for messages. I'm available.
Professor, I was curious because I know the code that I wrote, like the code itself, probably wouldn't do the job correctly for the programming section of the midterm. But like, like let's say like the bash file just makes it run, right? Like, how many like points would you estimate like I would gain from that if it just like runs and like outputs the text and everything like that?
Well, that's the blank level. The blank level, a program runs and just says, hello world, that's 20 points. But it depends on how much additional has been added to it beyond that level. So like very foundational level, the program runs and it says, hello, professor, have a great day, goodbye. That's a 20-point program and it's equivalent to the blank answer on the concept test.
Yeah.
But if you start doing additional parts of the program, um, like what was this? I'm looking back at this. Suppose in this payroll problem, all it did was to read in hours and pay rate and write back out hours and pay rate. Well, then probably it's 30 points. What if it read in pay rate and hours worked and computed it incorrectly? At least made an attempt to compute the gross pay. Well, maybe that's 45 or 50 points. If it actually produced correct results, then it's probably 80 or 90 points. So
Would it be okay if I shared my screen and just like showed you real quick?
sure, I'm glad to look. Sure, let's do that.
So let me know if is it working right now?
I see your screen. Yeah, that's good.
So these are the files that I have, and then like for example, when I do I believe what is it, shr.sh, like
Yeah.
like it runs for me. And then like if I do like this and then hourly rate, and then it just says the weekly pay is being computed. It doesn't actually compute it in the code, but like it runs.
Sure, that's significant. Nothing was computed that we can see. We're somewhere in the middle. At this point, I would. It's above the blank program, and I'd have to see more. I'd have to see the source code and see what has happened, and it's somewhere between 30 and 50 points, probably in that area.
Okay, all right, that's good. Thank you, Professor.
Sure, you're welcome. Okay. We are at 3:15.